We are continuing our notes for Unit 6, Section 6.1 on the central limit theorem. We have discussed the distribution of the sample mean. We have done a couple of applications and we will do a couple more in this last video for Section 6.1. The mean number of minutes for app engagement by a tablet user is 8.2 minutes. Suppose the standard deviation is 1 minute and we take a sample of 60. What is the standard error for the mean? The standard error is the standard deviation of the sample means, and that is equal to the standard deviation of your variable divided by the square root of n. The standard deviation for the variable, which is the length of app engagement by a tablet user measured in minutes, is 1. The size of the sample is 60, so 1 divided by the square root of 60. In my calculator, I will do this math. 1 divided by the square root of 60. And the answer is 0.129099. So let me write that. Approximately 0.1290994449. So for our purposes, we will say approximately 0.13. But again, when we are entering our values in ArtofStat, we want to enter all those digits. The distribution of the sample mean, because the sample is n equal to 60, which is greater than 30, that distribution will be approximately normal. It will have the mean as the mean of the variable, which is 8.2 minutes. And it will have a standard deviation, the standard error for the sample mean, which is approximately 0.13. And we will sketch our normal distribution curve, which is symmetric and bell-shaped, and we will label this to be the mean time for app engagement for samples of size 60 and measured in minutes. And they are asking us to find the 90th percentile for the sample mean. Again, the mathematical expression will be the probability, the x bar, which is the sample mean, to be less than or equal to this particular value, equals to 0.90 or 90%. So I'm going to use ArtofStat here. I have a mean of 8.2 and I have a standard deviation of 0.129, 0.99 and 4449. And they are asking us to find the percentile quantile of the lower tail, but at 90%. And the expression is up here. It is 8.365 is the value of the sample mean that is the 90th percentile. In English, this means that 90% of sample means from samples of size 60 will be 8.365 minutes or below. So that number is 8.365 minutes. Interpret the value, right? We just said the interpretation. Find the probability that the average app engagement is between 8 and 8.5 minutes. Don't forget to sketch here, I forgot it. So this was my 8.365. We will be asking you to shade the area of the curve that corresponds to the probability that you were investigating, and the percentiles have probability below them equal to the percent probability. For this current question, we want between 8 and 8.5 minutes. So this is 8 over here. 8.5 is approximately here. And they are asking us to find the probability within this area. So let's try to see how much that will be. The mathematical expression is, what's the probability? 8 less than the x bar, less than 8.5. And again, we are looking for the sample mean for samples of size 60. When I am in the Art of Stat normal distribution app, I want to go under find probability. I want to fix again the mean to be 8.2 and the standard deviation to be 0.129094449, and they are asking us to find the probability in an interval, and the interval is from 8 to 8.5. And again, remember that your variable is not x but x bar. We are talking about sample means from samples of size 60, and the probability that the mean is between 8 and 8.5 is 0.9293. or 92.93%. Our last example for this section refers on cans of soda. A cola beverage claims to contain 16 fluid ounces. The amount in a sample of 34 cans are measured, and the mean contents were 16.01 fluid ounce. If the cans were filled so that the mean of the process of filling them was 16.00 fluid ounces as labeled, and the standard deviation was 0.143 fluid ounces, find the probability that a sample of 34 cans will have an average amount greater than 16.01 fluid ounces. Do the results suggest that the cans are filled with an amount greater than 16 ounces? So the question here is, how unusual will it be if your average was 16.01 fluid ounces or greater? And this is one thing that we will be discussing in future chapters. That is because your sample is the only concrete data that you have, and the theoretical distribution, the company claiming that they have made their or configured their machines in a way that they will be filling the cans with 16 fluid ounces exactly, may not be valid. So that your question is whether an average from a sample of 34 cans of 16.01 is an unusual average. Unusual meaning having a very low probability of occurring if it came from that population. So the standard deviation is 0.143 and the mean is 16.00. So I'm going to go to my Art of Stat. So 16 exactly, 0.143. And we are looking for the probability of greater than 16.01. So that's the question that they are asking us. So the probability that the mean of 34 cans will be 16.01 fluid ounces or greater is 47.21%. Oh, I made a mistake here. So sorry. I didn't do the distribution of the sample mean. I did the distribution of the variable, but which is the contents of one can. I want to discuss the mean from 34 cans. So I could not use the distribution I just described. I have to do a distribution that has a different standard error, and that will be 0.143 divided by the square root of 34. So I'm going to do that math in my calculator, then I'll fix this again in Art of Stat. So 0.143 divided by the square root of 34 is this number, 0.0245242 977. Now, with this new standard deviation, I can answer the question about the sample mean. So the question is, what's the probability the sample mean will be greater than 16.01 fluid ounces? So let's put those numbers in again. 0.024242 0.24242 I think. Yes. And let's try this again. What's the probability we are greater than 16.01? And now the probability is 34%, rounded to the nearest hundredth of a percent. So 0.34 is the probability, the correct probability this time, or 34%. And the question is this unusual? The answer is, it is not unusual, because 34% is not unusual to come out of a population. Values that are unusual are those that have a probability of occurring at 5% or less. A mean of 16.1 or greater is not too far from the mean of the distribution of the sample means. So this is not unusual. That means that if the company claims that they have configured their machines to fill the cans with 16.0 fluid ounces as labeled with this particular standard deviation, we did not find any evidence to indicate that this will be otherwise. As a reminder, the glossary for this section is the central limit theorem that indicates that if you draw sufficiently large samples, then the distribution of the sample mean will follow a normal distribution, with mean the mean of your data, and standard error the standard deviation of your data divided by the square root of n. We talked about the sampling distribution, and we talked about the fact that the standard deviation of the sampling distribution of the means is called the standard error for the mean.